Stoichiometry in electrochemistry. You already know that coefficients in a balanced chemical equation represent mole ratios. When applying stoichiometry to electrochemical equations, we have to also consider the coefficients as they apply to electrons. For the half reaction showing the reduction of copper ions, we can read this as 1 mole of copper ions and 2 moles of electrons produce 1 mole of copper metal. Well, this is all well and good, but dealing with moles of electrons is a little awkward. We can convert moles of copper to a mass, but what do we do with the moles of electrons? British physicist Michael Faraday developed a way to deal with this in the 19th century. Firstly, we have to deal with some definitions and relationships among electrical quantities. Current, having the symbol capital I, is defined as the rate at which electrons are moving through a circuit, and is measured in amperes after a French physicist. Rate refers to an amount of time and is always measured in seconds. Because electrons are so numerous, our calculations would have to deal with ridiculously large numbers when considering them, so scientists have grouped electrons into clumps of a specific number that delivers a charge, symbol Q, of what amounts to 1 coulomb, symbol C, after another French physicist. So current in amperes, charge in coulombs, and time in seconds. Well, this is all very well, but where do moles of electrons come into this? We'll answer that by way of a question. What mass of copper is plated at the electrode of an electrolytic cell that has had a current of 500 milliamps applied for 1.5 hours? Now, there seems to be a very big leap between what we were just talking about and this question. But let's think about it. Mass is gained at the cathode. Ions in the solution form metals when combined with electrons at the electrode. The number of ions binding to the electrons will depend on the number of available electrons. According to the equation here, we see that 2 moles of electrons are required to turn 1 mole of copper ions into 1 mole of copper metal. Given the information in the question, I can determine the amount of charge in coulombs 500 milliamps can make in 1.5 hours. First, we'll arrange the formula so we have it in terms of Q. Then plug in the numbers and solve. There are 1000 milliamps in 1 amp, so 500 milliamps is the same as 0.500 amps. So that the units will cancel, I substituted amps for coulombs per second. To convert the 1.5 hours into seconds, I use seconds to hours conversion factor. So 2,700 coulombs of charge is sent to the cathode in 1.5 hours. If only there was some way we could convert the charge to moles of electrons. And there is. Michael Faraday discovered that relationship. Your book provides a little more detail, but basically we can convert this charge to moles of electrons by using the Faraday Constant from your data book as a conversion factor. For every 1 mole of electrons, there are 9.65 times 10 to the 4 coulombs of charge. Or 9.65 times 10 to the 4 coulombs of charge is delivered by 1 mole of electrons. That's a great thing about conversion factors. Either way works. Just make sure it's set up so that the appropriate units cancel and that the units you're left with are the units you're looking for. To calculate the mass of copper deposited at the cathode by the transfer of 0.02792 moles of electrons, we do a little bit of stoichiometry. To determine the number of moles of copper 0.02792 moles of electrons provide, our conversion factor is the 1 to 2 mole ratio from the half reaction at the top of the page. For every 1 mole of copper metal, 2 moles of electrons are required. Finally, the molar mass conversion factor to turn moles of copper into mass of copper gives us our answer, expressed here to the correct number of significant digits. This problem illustrates Faraday's law. The amount of a substance produced or consumed in an electrolysis reaction is directly proportional to the amount of charge that flows through the circuit. That means that increasing the time or current will proportionally increase the number of moles of electrons. Finally, using electrolysis in the industrial extraction of metals. The alloy in pop cans is about 97% aluminium. Canada produces about 2 million tons of aluminium every year. It's extracted from bauxite and aluminium ore by electrolysis. The amount of electrical energy used is so large that it significantly affects costs and where these extraction plants are located. Electrolysis is also used to remove impurities from extracted metals by electroplating them to the cathode. This is called electrowinning.